Okay, so here we are going to cover the section of properties of logarithms and natural logs. And what we need to do though is revisit a little bit the properties of exponents that was covered back in Algebra 2. So over here to the left of this box here is what I'm going to do, where I'm going to do that. So for instance, if you had two numbers with a common base, let's have this base be x. So x to the n power, and we multiply by another term that has the same base, x to the n power. What you would do when you're multiplying is that you would add the exponents. So x to the n plus n would be the situation there. Okay. That will, same manner, let's say you were taking those two terms and instead dividing them, you would write the base one time and instead now subtract exponents. I always tell students, think of the division symbol as a big subtraction sign, and you will transfer it over. Okay, so multiplication implies the addition of exponents, division implies the subtraction of exponents. So if you look over here to the right, logarithms are exponents. Therefore, if they are exponents, they should emulate the same properties that exponentials had. So here's what we're doing that in this case here. So you're taking a logarithm that has two terms that are two terms that are multiplying, and we're going to expand them into two logs that are adding, because multiplication implies adding in our properties. Okay, so you will expand it by making sure both terms have a log a with a base of a, and then take the first term and then the second term that was multiplied, add it to the second term that has a log. Quotient is the same thing. Let's say you had log base a of two terms that are dividing. You can expand that logarithm. The first term will go first as the first mentioned log, minus, and then log base a of v, which is the denominator. So the numerator always comes before the denominator. This last power property doesn't really emulate that much. Let's write the one for exponents. If you have a base raised to n power, and then there is an n, which is the power raised again, all you do is just multiply. So m times n. So what they're kind of doing here is the same thing. So you have log base a of u, and the u is raised to a power. Well, when you have a power raised to a power, we want it to multiply. So what they're doing here is they're taking this exponent that u is raised to, and they're making the exponent become a coefficient. Okay, and notice how it becomes a coefficient here. All right, so it moves from being in a power, and it becomes a coefficient, and n is next to log a base u, which is algebra for multiplication when they're side by side. Okay, so on the left hand side, that side is called the condensed form. So I'm going to write the word condense. And on the right side of the equal side, that is the expanded form. Okay, so you're going to notice later on when we're practicing, we are going to have examples that are written in condensed form that I'm going to want you to rewrite into expanded, and vice versa. So let's look at example number 1. Example number 1 is taking the log base 2 of x times z. So here we have a multiplication of two terms. So when I expand it, I know I'm going to add. So log base 2 of the first term plus the addition of log base 2 of the second term. With division, division implies subtraction. Again, I'm expanding, so I'm going from one log to more than one log, okay? Since it's only two terms, I'm going to have two log terms. So log base 2 of the numerator value minus log base 2 of the denominator value. Okay? Now, you'll notice that over here we had log base 2 of a variable, log base 2 of another variable, so there's nothing more to do when it comes to the simplification process. But over here, something changed. We have a log base 2 of y, nothing can be done there, but log base 2 of 8 can be changed, okay? So if you remember that that a logarithm is an exponent, you need to see if this logarithm can be rewritten as a numerical value. In other words, 2 to the what power would give me an 8. That's what you're asking yourself, okay? So if I rewrote that, okay, log base 2 of 8, basically log base 2 of 8 equals question mark. I'm basically asking myself, well, 2 to the what power equals 8. So that means my exponent is going to be a 3. So the value of that is actually equal to log base 2 of y minus 3. So whenever you can simplify, please do so. Let me move this over because you didn't see what I wrote. Log base 2 of 8 equals question mark. Means I don't know what that means. What is the value? And so I rewrote it from log into exponential form. 2 to the something power equals 8. And that's going to be 3 because 8 is the same thing as 2 to the third power. Over here, so let's talk about something back in the exponents property about radicals so that you would understand why I did what I did over here. So again, revisiting. Let's say I had something like this where a base was raised to a rational exponent, a fraction. The way you would rewrite it is into radical form is that whatever the numerator is, it's going to become the exponent of the base. So I'm ignoring this part, okay? That's what that part is. And the other part that I ignored is actually the value of the index of the radical of your problem. So that's what that is. This is equivalent to that. So you see this problem over here? I need you to rewrite this, okay? So instead of log base 2 of the cubed root of x, we're going to rewrite it as log base 2 of x. The exponent of the x here is an invisible 1, which is the m over here on the side. So there's an invisible 1, and over is going to be the index value over 3. So 1 over 3. Okay, so these two are equivalent to one another. Log base 2 of the cube root of x is the same thing as saying log base 2 of x to the 1/3. Why did I do that? Because I'm trying to have you see this problem like that. Okay, log base 2, so my a is 2 in this problem. X is replacing the u, the 1/3 is replacing the n up here in our property box. So what are we supposed to do is take that exponent and move it to the front. So 1/3 became the coefficient log base 2 times x. Okay, not times x, of x. Okay, and there's nothing else we can do with regards to that problem. So let's slip over here to example 4. Log base 2 of x to the third times y. So I actually have several properties going on here. I see two things are multiplying. So that means I'm going to apply the product property over here. And I also notice that there's an exponent, and anytime I have exponents, I move them as coefficient. Well, let's do one step at a time, although if you're comfortable, you can do it all at once, okay? So here we go. I'm going to split it up. I know this and this is two separate terms. They're multiplying. So multiplying means split them up and put an addition sign in between them. Okay? And expanding requires us to move exponents to the coefficient position. And because both of these are logarithms of variables, we're done. There's nothing else to do. Let's go in the reverse direction now. Instead of going from condensed to expanded form, we're going to take the expanded form, which are more than one log, and bring them together into one unified log. So let's go in the reverse manner. First thing I want you to do is make sure all coefficients become a 1. We do not want coefficients other than 1. So that has an invisible 1 here. This 5 needs to go. And when it goes, it becomes a power. So here we go. Log base 2 of x plus log base 2 y. That 5 became a power. Again, I want them together. This is still not a condensed log. Condensed means one log needs to be shown, okay? So plus means multiplication. Let me see if I could fit it right here in between the space. Log base 2. These have to multiply if I'm going to bring them together under one log. Okay? Let's do the same thing here again. I would pause the video, by the way, if you'd like, work it out yourself and then check with me, okay? All right, so hopefully you have now unpaused and you're checking your work. So let's move that coefficient. First step is log base 3 of y minus log base 3 of x. And let's put that up there to the 1/4, okay? Then the subtraction implies that we are going to divide. But you know what? Let's do this first. Let's rewrite x to the 1/4 as a radical. So I'm going to put the x to the invisible 1, and then I'm going to put a 4 out here. And now subtraction means division. Okay, so hopefully you can see that clear enough. Okay, so make coefficients be 1 and turn any coefficients that it's not a 1 into a power. Then I noticed there was a minus, but because that's a radical, not radical, a rational power, I decided to rewrite it as a radical. And I brought them together into a single log. Okay, so here we have more than one log. That addition means multiplication, and that means division. Always do it from left to right. I know I want only one log. So x, the log base 2x plus the log base 2y just becomes log base 2xy. But I know that I was going to subtract, which means division, and I'm going to put the z, and I'm done. In the next box here, when it has properties as applies to natural logs, you should observe that these are not going to be any different to what we did above. Okay? All you're just remembering is that instead of us writing log base e of uv, log base e is just ln, so the properties are not changing. Okay? So we're going to talk about change of base next. Okay? But before we talk about change of base, I need to bring a reminder a little bit of what we've done in the past so you would understand why we use this here. So I'm going to flip over. You can do the same and use the blank spot at the back of your page. If I asked you to evaluate, okay, the following. Let's make this problem number 1. Let's say I said log base 5 of 125. Okay, let's say I asked you to evaluate that. So, you learned in the past that what we do is we rewrote these as an exponential, right? So since I need to figure out what log base 5 of 125 equals to, I'm just going to set it equal to x and rewrite it as 5 to the x power equals to 125. Once I rewrote that, I saw that 125 was the same thing as saying 5 to the 3rd. And because of the 1-to-1 property, x is the same thing as saying 3. Okay, so that follows that log base 5 of 125 is equal to 3. Okay, now there's another way that you can rewrite it. Okay, and some students, instead of doing all that writing, write it like this. If I said evaluate log base 5 of 125, you can rewrite it like this. Okay, you want to achieve 125 in having the same base as whatever this number is right here. And we know from the previous property that 5 to the third is the same thing as 125. So if you start getting accustomed, you can just say, well, I know 125 is 5 to the third power. Okay, so log comes down, 5 comes down, and whatever this number is, write it here and try to find that number to what power gives me 125, or whatever number you see in that position. And the reason why you do that is because we know that log 5 of 5 is just a 1, okay, or log 10, 10, or log 9, 9, or log 12, 12. That's a 1. So I like to do this cheesy thing of saying, okay, I'm going to cancel those out, and I'm going to smile. It's called my smiley face deal. The 3 we know moves to the front, and we know that 3 times 1 is just a 3, and you're done. Okay, so let me practice writing it out with another one for you. Okay, let's say I said log base 3 of, what can I do? Let me find another one. Okay, let's do this. Log base 3 of 243. Okay, so let's do it the shortcut way. Log base 3 of 243 is the same thing as saying log base 3 of 3 to the what power? Okay, I want it to be a 3 so I can impose that smiley face thing. So I can try, okay, if you don't know it right off the top of your head, you can do, okay, 3 to the third power, I know it's 27. How about 3 to the fourth power? That's not going to work. 3 to the fifth power. Yep, that worked. So 3 to the fifth power. Yay, I'm happy. There's my smiley face. 5 is my answer. Okay, so why am I showing this all to you? Well, there's a problem. Log base 4 of 26. Okay? So what your goal is trying to get this to be a 4, right? So log base 4 of 4 to the question mark. So 4 to the what gives me 26? Well, let's see. Hopefully you already said nothing. But 4 to the 2 power gave me 16. 4 to the third power gives me 64. Yeah, it's not going to happen because from 2 it was a 16, which was lower than this. 3 went all the way to 64, so it's going to be somewhere trapped between a 2 and the 3, and obviously it's going to be a decimal. So this method won't work, okay? So that's where this next change of base formula comes into play. So let's flip over. Here's what I'm talking about that. So look at example number 8 with me. See how it says log base 6 of 8? Well, let's try and fix that. Log base 6 of 6 to the what power? Okay? Can't work. Can't do it. Okay? Can't do it. Okay? No common bases is what you basically should be telling yourself. Okay? So, what you're going to do is we need to find another method to do this, and that's where the change of base comes into play. Alright, so if you have this failing, what you're going to do is rewrite log base b of a as a division problem. So you literally are ignoring the b, so I'm ignoring the b, whatever that base b was, and I'm going to rewrite it in this form or in this form. I don't care which form you choose, okay? They both work. But what you're doing is you're changing the base of b, which is a 5, a 2, an 8, a 10, no, not a 10, sorry, a 9, a 12, and changing it to a 10 or an E. Remember, if it's written in log form without a subscript, it means it's a 10. If it's written in natural log without a subscript, it's an E. Okay? So, log base 10 of this number divided by log base 10 of the subscript, okay, which is the base. So we're going to do it over here. Since we failed to be able to do this process here in getting them the same, rewrite it as log invisible 10 of this number over log invisible 10 of the subscript. And you're done. Okay? And all you do is put this in the calculator. You don't have to, because I'm telling you to find the exact value. But if you wanted the approximation, I'll show you here what it would look like. You would just do the log of 8 divided by the log of 6. And we said it was trapped in between, what was it trapped in between? Anyway, I forget what oh no, that was the other problem, my bad. It's going to be 1.16, okay? And the reason was we were looking for 6 to the what power would be an 8. Well, we know that 6 to the second power is 36, and 6 to the, to the 1 power was a 6, and we needed an 8. And so 8 is trapped between 6 and 36. Therefore, our exponent was trapped between 1 and 2. So that's how you got this answer right here. Let's try this one here. Is there a way of rewriting this as log base 2 of 2 to the something power, where 2 to the something power would give you square root of 3? No, it's not possible. So we would use change of base. Log base 10 of square root of 3 over log base 10 of 2. Or if you wanted to use natural logs, you can do the same thing. ln natural log of square root of 3 over the natural log of 2. To prove to you that either one works, look how they're the equivalent. Log of square root of 3 divided by log of 2 gives me 0.499. Let's use natural log instead. Natural log of square root of 3 divided by natural log of 2. And, oh my goodness, I typed that wrong. So sorry. Let's try that again. ln of square root of 3, arrow out of that, divided by ln of 2. There we go. So, am I messing up again? Oh my, I didn't type it right over here in the first place. Wow, okay, let's try one more time. Log of square root of 3. Okay, I'm definitely showing you what not to be doing. When it comes to typing, divided by log of 2. There we go. Those are identical. Okay? All right. So let's go here. So let's practice. 2 to the x equals 2 to the 2 to the x equals 15. Is there a way to get common bases here? Okay? So can I rewrite 15 as 2 to the power of something? So like 2 to the x equals 2 to the something power? No. 2 to the nothing will give me 15. Can't do it, right? So I'm going to put a big nope. So when you can't do that, write it in log form. So let's rewrite that as, log base 2 of 15 equals x. And then change of base tells us to rewrite it as log of 15 over log of 2. Let's try this over here. Let's see if we're able to rewrite this with common bases. Well, first we have to get rid of that 3, and we'll divide by 3 on both sides. And when you do that, you're going to get 2 to the x equals 14. Well, can I rewrite? I'm going to come up here because I'm running out of space. Can I rewrite 2 to the x equals 2 to the something power, where 2 to the something power makes 14? Well, let's see. 2 times 1 is 2, 2 times 2 is 4, 2 times 3 is 8, 2 times 3 is 8, 2 times 3. 2 to the third power is 8, 2 to the fourth power is 16. It passes it. We don't have anything to the power 2 to the raised to the power to give me 14. So again, change of base. Notice that 2 to the x equals 15 was rewritten like this. So you did log 15 over log 2. And so you can rewrite this, but if you already see the pattern of writing it in change of base form, you can do so and skip this step. But rewriting this in logarithmic form, you get log base 2 of 14 equals the x. And so that's going to be the same thing as saying log of 14 divided by log of 2. Okay. How about here? Notice this is a base of 3 and that's a base of 9. Can we get the bases to be the same? Well, oh, thank goodness we do. So let's rewrite 9 with a base of 3. 3 to the what power makes 9? 3 to the second power. So here is a case where we will not need change of base. We can apply the one-to-one property, leaving the exponents, and solve for x. Subtract 1. And then solve for the x by dividing both sides by 4. So x is 1/4. So in this case, we did not need to use change of base because we were able to get a common base of 3. How about over here? Are we able to get a common base? 4 to the what power will give me a 7? Not possible. So straight away, log 7 over log 4 is going to be our x. Here, I need to solve for x. Well, all I need to do is get rid of plus 7, right? So let's just move it to the other side. 2 log of 5 of 6, not of 5, 2 log base 5 of 16 minus the 7 that came over equals x. I try to simplify this. Can 16 be rewritten as 5 to something power? Nope. So we just leave it in change of base form. And we're done. And last but not least, we love these problems because if you notice that you have common logs, just like you were able to cancel out common bases, you can also cancel out, because of the one-to-one property, common logs. So all you're left with is x plus 4 equals to 29, and x is solved for by subtracting 4 on both sides, and x equals 25. And we are done.